Yes, this is online class 4. We're going to cover section 4.4 multiplication rule today. The basics, and this is for class on Monday, September 24th, fall 2012. Multiplication rule. Let me motivate today's lecture. I always like to have a motivating example between before new topics. Let me give you a 2-question quiz. Let's say in this quiz you've got a true-false question, and in the second question you've got a multiple choice with choices A, B, C, D, and E. Let's say I randomly select 2 answers from both questions. All right, so I know nothing, and I'm making random guesses on both of these. I'm going to ask you, what's the probability that both questions have been answered correctly? All right, I think we can easily consider this using a tree diagram. If you've got true-false possibilities in the first question, and we can see that it's going to trail through to 5 other responses in the second question. Similarly, for the false response in the first question, you'll trail off to 5 other possibilities in the second question. Clearly, we can see there are 10 paths from left to right, hence 10 possible outcomes, 10 possible test papers or quiz papers I might view, and only one is correct. Only one has both questions correct. So it's an easy thing then to state that the probability that both questions are correct is going to be 1 out of 10, or 0.1. Alright. Now, we can't be drawing tree diagrams out all the time, especially with the more complicated problems. Things get a lot more cumbersome, especially with tree diagrams. So let me suggest another way to grind out the probability of both correct in this scenario. The probability that both questions have been answered correctly. I can rewrite that event in this fashion. It's the probability that the first one is correct and the probability that the second one is correct. And I'm going to suggest to you a rule that says, well, when we see the word and, we can multiply the corresponding probabilities, and I can say it's the probability that the first is correct times the probability that the second is correct. So I want you to remember, when you see and, you think multiplication rule, as in this example. I think you know where we're headed here. The probability that the first question has been answered correctly is 1/2 times 1/5 the probability that the second has been answered correctly, and that's 1/10, or 0.1, and we get the same answer as with our brute force method. This suggests a rule in general that the probability of A and B equals the probability of A times the probability of B. I call this the multiplication rule for AND type compound events. Alright, I want you to turn to example 1 on page 161. Involves the polygraph study data that we've looked at before. So please pause now, turn to that page and that example on that page, and take a moment to refresh your memory in this regard. Please pause. Alright, back we are. I'm going to write out this data for us, and you know the drill. The rows indicate whether the polygraph machine said you lied or not, and the columns indicate indeed whether you lied or not. Right, from this study, we recall the grand sum was 98 in this example. I'm going to pick two. Pick two subjects randomly. Alright? And I'm going to say without replacement. Now that means you pick one, you throw it back, and you pick another one from the available pool. I claim the probability that, well, let's see, the example asks us for this probability. The probability that the first one has been chosen as a positive test result and that the second one chosen had a negative polygraph test result. Alright, I claim, according to the multiplication rule, it's the probability that the first one was chosen positive times the probability that the second one was chosen as a negative test result. But we've got to make an adjustment here in this second slot. Let me show you what I'm talking about. If we pick the first one, positive, well, we've got 57 possible positive tests divided by 98 subjects. Alright, so that's the probability that the first one is positive. How about the probability that the second one is negative? Well, we've got one less to choose from because we're picking these objects, these people, without replacement. So I must make an adjustment to the multiplication rule in this situation. Alright, so I've got 97, one less, 97 to choose from in the second trial, and 41 of those had a negative test result. So if I grind that out, cursor down, I get a 0.246, and let me make a little note here, must adjust pools and selections down the line for without replacement, for situations where you're making these choices without replacement. Alright, let me be a little bit more formal here. I'll say events A and B are independent if occurrence of one event does not affect the probability of the other event. Alright. Well, I think you can appreciate if you're making selections are made with replacement. Well, that's kind of a code word for independent events. Simply because you're throwing independent events, simply because you're taking your first draw and throwing it back in the available pool. So selections made down the line are not affected because of this with replacement. Alright, so again, learn to appreciate that when you see the word with replacement or the words with replacement, a little bell should go off indicating that these events are indeed independent. Alright, if draws are made without replacement, well, that's really a code word for not independent events, just like it was in the last example we did. Alright, we chose those lie detector subjects without replacement, and we saw we had to make changes down the line. Let me give you another example here. Let's see, I want you to turn to example 2 on page 163. Pause here for a minute. Please turn to this example and refresh your memory, or refresh yourselves with the given information, and then come back and we'll work out the example. Please pause now. Alright, basically we've got this scenario here. We've got 5 available pacemakers. 3 of them are good. 2 of them are defective. Alright, the author asks us here, well, we got a part A and B. We randomly select 2, and that's with replacement. And again, when I see with replacement, I think independent events. Find the probability that both are good. Well, that's the probability that the first is good, and the probability and that the second is good, right? When I see an end word, the bell goes off, and I think multiplication rule. I suppose we don't always have to be so formal here. It's the probability that the first is good times the probability that the second is good, but I'm guessing you knew that. Alright, well, we've got 3 out of 5 are good, so the probability of the first being good is 3/5, and because of the replacement, the probability the second one is good is also 3/5, and if I multiply this out, I get 0.36, right? I contrast that with part B. Now part B asks us to randomly select 2 without replacement. Alright, so we're going to have to make some adjustments down the line. The probability that both are good. Well, I claim it's the probability that the first one is good times the probability that the second one is good by the addition rule, but we must adjust the second fraction, the second probability, because they are not independent events. Why are they not independent? Because we are making these choices without replacement. Alright, I think you know where we're headed here. The probability that the first one is good is 3/5, and the probability the second one is good is 2/4, and if I multiply that out, it's 0.3. And that certainly is different than the 0.36 we got in part A. So certainly, whether or not things are independent or not may have an effect. Alright, I want to look at now at example, let's see, actually this is exercise 22 on page 169. Alright, please pause, turn to this page and turn to this exercise, homework exercise within that page, and familiarize yourself with the problem statement. Then come back here and we'll work it out for you here online. Please pause. Alright, back we go. We've got 400 of these objects. 392 of them are good. 8 of them are defective. The book asks us if we randomly select 3. Find the probability that all 3 are good. Well, I'm going to do it 2 ways, and I'm going to illustrate something here. It's going to be a kind of a major rule that's going to help save us time in problems of this type. First, I'm going to do it without replacement. Alright, so the probability that the 3 are good, that's going to be the probability that the first one is good, which is 392 over 400, times the probability the second one is good. Now again, these events are not independent because we're doing things without replacement. You've got to reflect your reduced pool as you make picks down the line. So we've got 1 less to choose from and 1 less good one to choose from, right? So 2 adjustments there, and the probability that the third one is good is then going to be, and still 1 less, 398 left to pick from, and only 390 of them are good. If I grind this out on my calculator, now please bear with me, I'm going to write this out to 10 decimal accuracy. I'm doing this for a reason. Alright, I want to contrast that when I'll do the same problem. Randomly select 3 and find the probability all 3 are good with and here now I'm going to do it with replacement. And the probability that 3 are good in this situation, well, I'm going to have 3 fractions multiplied, and they're all the same, so I'll just raise them, that one fraction, to the 3rd power, right? Because I'm doing things with replacement, this probability is not affected as I make choices down the line. So if I grind this out, my calculator returns this answer, and they're almost the same. Well, they're the same to at least 3 decimal places. Well, the idea I'm getting at here is sometimes if you assume independence, if you assume you're doing things with replacement, you often get the same or almost the same value, a good enough value, as computing it without replacement. Alright, let me get a new layer here. Oops, hang on a minute. Alright, there we go. Add a new layer. Alright. Alright. The book cites what we call a 5% guideline. Now, what's that? It says if the sample that you're picking is not more than 5% of your available population, it's okay to assume independent trials or independent selections or independent events, even though technically they're not. And again, when we're assuming independent events, we are assuming we're doing things with replacement, because it makes our calculations so much easier, and the answer is almost as good. Alright, I want to do exercise 30 in our text, and give me a minute here. I believe it's on page 170. Yes, exercise 30, page 170. So please pause now, review that question, and get familiar with its given information, and we'll come back and work it out. Okay? Please pause now. Alright, we're back. Let's see, we've got similar scenario as exercise 22. We've got 200 items, 195 of them are good, 5 of them are defective. Alright. Well, part A asks us, well, the statement of the question says, a quality control analyst randomly selects 3 different car ignitions from a manufacturing process that has produced 200 systems, including 5 that are defective. Let's look at part A. Does this selection process involve independent events? And the idea is no. That's implied. They don't really state that in the problem. That's implied by the word different. He's picking 3 different ignition systems. Alright? So, alright, we'll assume the author's implication that these are not independent events. Alright, part B says, what is the probability that all 3 ignition systems are good? And they tell us, do not treat the events as independent. Well, similar to the last example we did, the probability that 3 are good is going to be 195 over 200 times 194 over 199 times 193 over 198, adjusting my probability factors as I move through my selections, right? Just as I should for not independent events. If I grind this out to 3 decimal places, I get 0.926. Alright, part C says, use the 5% guideline for treating the events as independent and find the probability that all 3 are good. Well, your sample size, here it's 3, you're picking 3, is not more than 5% of your available population, 200. Of course, 5% of 200 is 10, so certainly 3 is not more than 10, so it's okay to assume independent selections. Alright, so I'll work this out. Makes it quite a bit easier. The probability that all 3 are good, well, it's the probability that 1 is good, which is 195 over 200, multiplied by itself 3 times. Well, basically I can shortcut it by taking 195 to the over 200 to the 3rd power, and you'll notice I get pretty much the same answer with a lot more button pushing in part B, right? And you can see this problem even gets worse when you start talking about picking 4 or 5 or 7 or 200. This brute force method of changing all these fractions is greatly simplified by this 5% guideline. Okay? Alright, one more topic I want to talk about before we call it a day in this section. Now, it's example 6 on page 166. So please take a minute to pause and acquaint yourself with the statement of the problem, and come on back when you're familiar with the problem statement and we'll work it out for you. Alright, here we go. Example 6, page 166. You're talking about a plane and probability of failures of electrical system within plane. Alright, we're given this statement that the probability of an electrical failure at any given time in any engine is 0.001, 1 out of 1,000. Okay, that information is given to us. Now, part A, you're in a one engine situation. If the engine in an aircraft has one electrical system, what is the probability that it will work? Well, the probability that one electrical system works, well, it's going to be by the rule of complements. They give you the failure, the probability of one electrical failure is 0.001. Let me be a little bit formal about this, at least this first time out. I'll say the probability that one electrical system works is 1 minus the probability of an electrical system failure. And I'll abbreviate it somewhat casually. Alright, well, of course, that's 1 minus 0.001, and if I grind that out, it's 0.999. Alright, so that was pretty soft. How about part B? Let's say a plane has 2 electrical systems. And they ask the question, if the engine in an aircraft has 2 independent electrical systems, what is the probability that the engine can function? Well, the engine can function if one of these electrical systems works, one or the other. Let me write that down. I'll say engine will function unless both electrical systems fail. Right, remember, the engine has two. Right? The plain engine. Let me stick that in there. Right. Plain engine has two electrical systems. Alright, the engine will function unless both electrical systems fail. So I'm going to say it like this. The probability that both electrical systems fail, and that's a bad thing, I claim it's going to be the probability that the first fails and the probability that the second fails. Okay? Well, because they're independent, the book explicitly tells us these are independent electrical systems. So this is going to be the probability of a first failure times the probability of a second failure, and they're both going to be the same. We're assuming these engines' electrical systems are independent. And if I multiply those two together, 0.001 times 0.001, I get 0.000001. Now we're not done yet. This is the probability that both electrical systems fail. Now we want, what's the probability that the engine will fly, or that the engine works? The probability that the engine works, well, I claim it's 1 minus the probability that both electrical systems fail. Right? It's the complement, right? So I'll do 1 minus, let me get my eraser here, 1 minus 0.000001. Whoops, my pen slipped. Let's make sure I count my zeros right. 0.000001. And if I make that simple subtraction, I get 0.999999. Right? And we can see the answer to part B right here is, well, rather higher, certainly greater than the answer in part A. Not by much, but this illustrates the effect of adding an independent system onto the plain engine. Certainly, the more electrical systems you have, the more independent electrical systems have, the greater your probability of maintaining your flight and safety and life in the air. Okay? Alright, I have finished section 4.4. I'll end the lecture here, and please review Angel for your reading assignments, homework, exercises, and of course the online exam, which will be due Tuesday, September 25th at midnight. Okay? Alright, so we're all familiar with the system, so I'm going to end now.